looking at modelling current, what's actually happening in the wire. We're going to be meeting this new equation, which is I equals nQVA, and we're going to use that really to explain the properties of the wire and explain the current in the wire. It says in the specification to explain a large range of resistivities, but we'll meet resistivity later, and it's not that important yet. It will be, but not yet. Okay, so let's start with what's actually happening inside a wire. What do you picture in your head? So what I would normally get people to do is actually in small groups to role play this. But we're not in small groups right now. So you can just have a think for a second. What would you say? So normally when we do this, I have some groups saying, oh, well, we've got the charges in the wire, and if we've got a positive end and a negative end, and then they move through the wire, and everyone's happy. And then other people point out, actually, the charges that we're talking about are electrons, so actually they'll be flowing the other way. Not conventional current, that's what they'll actually be doing. And then the people think, oh, okay, but that would be like there's nothing there in the wire. There's also all of the positive charges, the ions in the metal. So, you know, if they're positively charged and the electrons are negatively charged, how are they moving? And it ends up with the realization that we haven't ever really talked about what's going on inside the wire. So this would be my first way of thinking about it. You start off with what you know about metals already. So we have the positive charges, the positive ions, and then the outer electrons are loosely bound and they become free electrons, and they're what moving around. So these delocalized or free electrons. And, well, on average, there's about one free electron per atom. It's not always true, but we're going to make that assumption right now. The next thing is that these free electrons are moving at random. So in this diagram here, this one might be moving this way, this one might be moving this way, all over the place. And they're actually moving really, really quickly. They're moving at about 1,000th of the speed of light. Now, obviously, that's a lot less than the speed of light, but that's still about 300,000 meters per second. Now, that should already be ringing alarm bells for some of you, because you've probably heard lower down in the school that although when you turn a light on, it seems like the electricity instantly causes the light to turn on, the actual flow of the current, we've said, is pretty slow. Certainly a lot slower than that. I know at GCSE we talk about, if I move my finger here, you know, the current may be moving about this sort of speed through the wire. And actually that's a nice time for an aside. So why does the light come on immediately if the current's flowing quite slowly? And it's because the current is, well, the charges are all there in the wire, a bit like a hose pipe that's full of water. When you turn the tap on, the water comes out instantly because the water's already in the pipe. Same with the current in the wire. So how can we deal with the fact that I'm saying that they're actually moving at about 300,000 meters per second? Well, it's because of this random motion and the fact that they're colliding with the ions inside here. So each of these individual movements will be at about 300,000 meters per second. See if I can show you what I mean. Actually, you might want to take this down as well. So in a metal, a conductor, the free electrons are constantly moving. They're moving at random, a bit like in this picture here. But because there's so many of them, and they're moving at random, over time, their displacement will basically be zero. There's no net movement of these things. I mean, if you looked at one individual electron, you might find that it moves slightly more to the right than to the left, and it sort of gradually moves over. But because there are billions and billions of these charges moving around at random, overall, they don't go anywhere. Let me just move this so you can actually see what's on the screen. Whoops, sorry about that. Yeah, so over time, the overall displacement is 0. So I would take this down. This is going to be useful in a little while. Right. So, if you open up a textbook, let's move this, you might see something like this, a picture showing what's going on inside a wire. We've got our electrons here, and they are drifting towards the positive end. Now, this is something we've not really talked about too much before at GCSE, and it's why that's actually happening. So this is connected to the positive terminal of the cell, and this end is connected to the negative terminal, and that basically sets up an electric field across this, which causes them to move. But this diagram's not right. Although they are tending to move this way, it makes it look like each electron is just moving right. But that's not happening. What this diagram should be more like is something like this. That the electrons constantly are moving between the ions, colliding with them. Now, this one's moving this way to the right, moving up here, moving up here. It looks at first glance like it's moving at random. But because there is this electric field here, there is a constant force moving them slightly to the right. So if you look at this individual path here, although it's moving between this positive ion to this positive ion, as it moves, it started heading off this way, but because of the electric field, it feels a force to the right, and it tends and it curves to here, and it collides with this ion and bounces off. And it would be heading up in this direction up here, although it now feels a force to the right, which curves it over slightly this way. It bounces off, or reflects off this one after the collision, would be heading straight up, but the electric field causes it to bend to the right again. I'm kind of saying that over and over again, aren't I? Sorry. So what happens is they don't zoom to the right, they drift to the right. And so you get an overall slight movement of these electrons. They drift along. And this velocity, this overall velocity, is called the drift velocity. So if I was you, I would sketch this and take note of these points. Okay. Now there's one other thing here that can cause a little bit of confusion, which is that, well, these are in this electric field. I've just realised I maybe haven't mentioned this, that the electric field is pointing, in this case, towards the negative end. Electrons, because they're negatively charged, experience a force making them move the other way. Okay, now, these electrons are constantly experiencing this force, so they should be accelerating, getting faster and faster and faster. And that would be the case if it wasn't for all of these collisions. So this is accelerated that way, it collides with this ion, it reflects back this way a bit, but the force then makes it come to the right again. The overall effect is that the drift velocity remains constant. Okay. So we've got drift velocity. Now we're going to relate that to the actual current in the wire. So we're going to start with this somewhat complex looking diagram. And if I was you, I'd pause this and I would sketch it carefully. And as you sketch it, try and think about what it's saying and then I'll talk you through it shortly. Okay, so what we've got here is a wire with electrons in it. And instead of saying exactly how many electrons we've got, we're going to quote this number n, which tells you the number of electrons per cubic metre of a wire. Which means that if you can work out a volume of the wire, you can work out actually how many electrons you've got. Now, these electrons are drifting to the right at velocity v. So here you go, it says the sea of electrons is moving to the right with drift speed v. Now, in a minute, we're going to try and work out what the current is. And if you remember that current is the amount of charge past a point in a second. Now, we could get that from this information because, well, in time t, all of these electrons here will have moved past this point, and the amount that will have moved past this point would be equal to the distance they've travelled in that time multiplied by the area of the wire. Basically, it would be the volume of this shaded area. So the volume of the shaded area tells you the number of electrons that have gone past that point in a particular time. So you might want to pause that or rewind that and think about that again, and then we're going to start using this and break this down to try and get an equation. Okay, so I'm now going to step you through this. Now, as I said a second ago, the shaded area is the length of wire the charge is passed through in time delta t. So that's this little bit here. So if they're going at a particular velocity v, that distance that they move through is going to be equal to the drift velocity multiplied by the time delta t. We're going to just park that for now and then look at something else first of all. In the first bit, I'm just going to move the picture up here, is that we probably want to determine how much charge would be in that shaded area, because that's going to equal the amount of charge past the point in the particular time or in a certain time. So how can we do that? Right. Well, the amount of charge is going to equal the number of charges, or the number of electrons per cubic metre. That's this little n. So number of charge carriers per unit volume, multiplied by the volume of the grey area. And then that would just give you the number of electrons, but we want the number in coulombs. So we need to multiply this by the charge on the charge carrier. So basically the charge of an electron, or 1.6 times 10 to the minus 19 coulombs. So this expression is going to tell us how much charge is in that volume there. Now, we said earlier, and it's written up here, but I'm going to break it down ever so slightly, that the volume is going to equal the area multiplied by the distance the charges move through in that time. So that's the A times delta x. And that should be fine. Now what can we do with this? Well, if you remember, our definition of current is delta Q over delta T. So what we're going to do is we're going to divide this expression, both sides of it, by time. So I'm going to put delta T on this side, and I'm going to put delta T on this side, just because I can. Now, what this means is that this expression here is now current. So that equals the current in the wire. I'll just just scroll down a little bit, sorry. So it looks a little bit neater there. And what I've highlighted now is that if this part on the left is the current, we've then got N, the number of charge carriers per unit volume, multiplied by the area, multiplied by the charge on the charge carrier. And then if you notice, we've got that length x divided by time. That is the same as this velocity, because the drift velocity is going to be delta x, sorry about the writing, over delta t. So this expression becomes the current is the number of charge carriers per unit volume multiplied by the area of the wire multiplied by the charge on each of the charge carriers multiplied by the drift velocity. I equals nAqv, which was from the beginning of the lesson. I'll just skip ahead. And you might want to take this down. You also will probably want to go back to the previous slide, so rewind a little bit and step yourself through that derivation and see if there are any parts you don't understand. Okay, now that's done, what we can do is just sort of find out, well, how fast are these electrons moving in the wire? So I've got a little challenge for you, I hope. Here we go. Right, this is your final task for today. What I'd like you to do is find out the drift velocity in a copper wire that's carrying 1 amp if the wire has got a cross-sectional area of 1 millimetre squared. Now, if we assume that there's 1 electron per atom, the charge density, that's N, will be 8.5 times 10 to the 28 per metre cubed, which is just a huge number. So can you use the equation, rearrange it? The drift velocity is I over nAq, and work out how fast they're going. Be careful though, because you've got to change this to meters squared. It's not just a case of 1,000 this time, is it? 1 millimetre squared is 1 times 10 to the minus 6 metres squared. Okay, let's see how you got on with that. So I've got some rough working out here. Rearrange it. Okay, so the drift velocity is the current divided by nAq. That's going to be 1 amp divided by 8.5 times 10 to the 28 times 1 times 10 to the minus 6, that's the cross-sectional area, times 1.6 times 10 to the minus 19 coulombs. The drift velocity comes out at 7.3 times 10 to the minus 5 metres per second, about 0.1 millimetre per second. That is how fast the electricity is going through the copper wires in your home. It's remarkably slow. Next time, we'll look at how we can use this equation to understand various problems. Have a good day. Bye-bye.